Hi y'all, Raya here, and today we'll be talking about how to solve for a very special type of differentiable equation called separable equations. These guys probably look a little bit intimidating on paper, but once you get the hang of it, everything will go down nice and smoothly. So let's throw out all the further ado and begin. Let's start with the basics. As I'm sure you've seen many times already by now, this dy dx represents the change of y over the change of x, or in other words, the slope. As the mathematician Leibniz would put it, d represents an infinitesimally small delta, or change. While I'm sure you've seen the slope as a function of x written differently, say, as the form of f prime of x, Leibniz's notation becomes much more useful than certain others when you start getting into some of the more complicated differential equations. For example, in our first problem. Question number 1. dy dx is equal to 2x over 3y squared. Solve for y as a function of x. So, what is this equation saying? Well, as we've stated earlier, this first term is the slope. As for the second term, it's just a relationship between x and y. In other words, this equation defines a graph by the slope at any given point, much like you may see in slope fields. As such, chances are that this equation defines multiple different possible graphs. But how do we go about tackling this problem? Well, if you're algebraically minded, you may have noticed that by cross-multiplying, you can put the x and dx on one side of the equal sign, and y squared dy on another, like this. The rigorous proof on how you can do this is probably a little harder to describe out, but thanks to Leibniz notation, it becomes much clearer on how to separate this function. And separate it we did, for this is essentially the definition of a separable equation, a differential where you can split up a function as a function of x, dx, times a function of y, dy. Now, here's the really interesting part. In this format, you can actually integrate both sides of the equation. I know it seems a tad bit iffy, but the proof of doing this isn't really that hard either. You can try it out yourself in my worksheet, which I'll helpfully link over here. So, now that we have an indefinite integral on both sides, the rest is everything you know already. Y cubed plus some constant c1 equals x squared plus a different constant c2. And, hey, since the c1 and c2 are both arbitrarily defined constants, i.e. they can be equal to anything, we can combine them as a single new constant, which we'll just call c. And there's our answer. Y is equal to the cube root of x squared plus some constant c. Whew, alright. Let's see if we can try a harder one. Question number 2. dy dx is equal to 2y cosine x. This can't be too hard. First, we'll separate the two variables. So this becomes 1 over 2y dy equals cosine x dx. Then we can integrate both sides just like before, and the right side should be easy. We just have the indefinite integral of cosine x dx. So that's just sine x plus some constant. On the left, we can solve this by using u substitution. U equals 2y, so du equals 2 dy. This becomes 1/2 ln 2y plus another constant, c1. As with the previous case, we'll move c1 over to the other side and multiply both sides by 2. This yields ln of 2y is equal to 2 times sine of x. And then again, these two are ambiguous, so we can just put them together in one new constant c. If we take e to the power of both sides, we can get 2y is equal to e to the power of 2 sine of x plus c. And by dividing by 2, you get this. However, we can go further. Check out this nifty trick. Exponents laws tells us that this plus c can be pulled out as e to the power of c times e to the power of sine of x, 2 sine of x over 2. However, c is an arbitrary constant, so as a result, once more we can arbitrarily let e to the power of c be rewritten as another constant. This time, we'll call it k. Hence, we get y is equal to k times e to the power of 2 sine x over 2. Okay, last question before closing off. The graph of f of x has a slope equal to y squared times the square root of x at any point x comma y, and the graph of f of x hits the point 4 comma 1. Solve for f of 9. Interesting. Although it may not be at first intuitively clear what to do, may I draw your attention to this. Yup, it's your best friend, dy dx, back to save the world. While the problems earlier were both about the symbolic representation of separable equations, here's one where you're going to be applying it to a function, a graph. So let's get this going. Dy dx is equal to y squared root x. So the integral of 1 over y squared dy is equal to the integral of root x dx. Finding the antiderivative, we get negative 1 over y plus some constant c1 is equal to 2/3 x to the power of 3/2 plus another constant c2. We'll move the constants and do a little algebra trickery to get negative 1 over y is equal to 2x3 to the power of 2. These two come together again, new constant c over 3. Y is equal to negative 3 over 2x3/2 plus c. But wait, there's more. Because we have a point, we can actually plug these numbers in and solve for c. So 4 is equal to, or actually, 1 is equal to negative 3 over 2 times 8, or 16, plus c. To make the denominator negative 3, we just have to let c equal to negative 19. We can bring negative 19 back into our original equation over here. And now we can just plug in 9. F of 9 is equal to negative 3 over 2 times 27, 54, minus 19. Or negative 3 over 35. Booyah! Alright. That's the end of this video then. If you need the practice, worksheet and answers are in the description below. Thank you, you glorious human beings, for getting all the way through that spiel. And, unless you went and skipped to the end. In which case, okay. Then, why did you even click on this video if you weren't gonna learn the stuff I was saying anyways? Whatever. I'm sure you had good intentions. Okay, this is Roy Yan signing out. See ya.